Hello everyone, welcome to my number theory lecture. So in this lecture, we continue to study linear combinations and we begin with the following theorem. If A and B are integers and the greatest common divisor of A and B equals D, then A over D and B over D are relatively prime. It seems, they're pretty obvious, right? But let's go ahead and prove this. Theorem. Uh, the statement is what? A and B are integers. So if A and B are integers, and the greatest common divisor of A and B equals D, then A over D and B over D are relatively prime, right? Proof. Since the greatest common divisor of A and B is equal to D, right? We know AX plus BY equals D for some integers XY, right? As a matter of fact, this is by the very first theorem, right? Very first theorem of this lecture, okay? Right. And also this is what, another way of saying like there exist two integers x and y such that ax plus by equals d. Okay, right. So I'm going to divide this equation by d. Then, so this implies a over d x plus b over d y equals 1. Okay? Now this is a legitimate equation because D is greatest common divisor of A and B. So it is a divisor, common divisor of A and B. So A divided by D, that's an integer. B divided by D, that's another integer. So that's what I mean by it is a legitimate equation. Okay, right. And so what this implies is, using corollary to the theorem, right? The very first theorem I was talking about. Since this equation is satisfied, so that implies A over D, B over D are relatively prime. Okay, relatively prime. So this is it. That's the end of the proof. Okay. next, here is an example. Find the solution of the equation 9x plus 24y equals 15. Okay, right. When we know how to do it, we already know how to find a solution of this equation, right? Using what is that? Euclidean algorithm, right? Example. Okay, so find a solution of 9x plus 24y equals 15. Okay, so here is a solution. First, we gotta find the greatest common divisor of 9 and 24. To do that, okay, so 24, if you divide the 24 by 9, so 9 times 2 equals 18. So, 18 plus 6 equals 24, right? So we get this one. And now, if we divide the 9 by 6, right? 9 by 6, so 9 equals 6 times 1 plus 3. So we see that this 3 is the GCD. Okay, so here the greatest common divisor of 9 and 24 equals 3. Now we are ready to find a solution of this by working backward of this, process, right, which is called the Euclidean algorithm. So actually, in this case, the steps are pretty short. So now we're going to work backward. So 3 equals 9 minus 6 times 1. And 6 equals, in the previous step, that was, the 24 minus 9 times 2 and times 1. Okay, so we get 9 and negative, positive, the 9 times 2, so we have 9 times 3, and then my plus 24 times negative 1. Okay, so here x prime equals 3 and y prime equals negative 1 as a solution of the equation, or to the equation, doesn't matter, right? But of, I used the of there, so of the equation 9x plus 24y equals the greatest common divisor of these two numbers, 3, right? Now, since 3 times 5 is 15, okay, so the x equals 5 times x prime. So basically, actually, I'm showing you the proof of what is that? The very first theorem. Okay, I mean that's the idea, right? Uh, anyway, so that's going to be 15, and y prime. No, not y prime. Y equals 5 times 5 times y prime, which is 5 times negative 1, so negative 5 is a solution of 9x plus 24y, the original equation, equals 15. So done. So we found a solution, okay? 15, negative 5, that's a solution of this. So here's a question. We already know this, right? So there's nothing new. I mean, using Euclidean algorithm, you can always find a solution. However, like I said before, this equation not only, has like what, one solution always, but it does have many solutions. In fact, what, how many? Infinitely many solutions. Okay, infinitely many solutions. Right. So how do we find like all the solutions of this equation? That's the big question, right? Okay, so that's what I'm gonna talk about next. So here's theorem. Oh, sorry. Suppose that a and b are non-zero integers and c is an integer, and let x naught and y naught be a particular solution to ax plus by equals c. Okay, here that a particular means that just a solution, all right? So not really nothing particular about the solution, just any solution, okay, a solution. But here a particular solution is a particular solution versus a general solution. General solution means uh, the, which represent like all the solutions, right? Okay, so that's what I mean by particular solution. Anyway, yeah, in fact, this word like a particular solution, you might sound familiar if you have studied like the differential equations, right? Yeah, so that's where also this terminology appears. Anyway, in that case, all solutions to ax plus by equals c are given by the following thing. X equals x naught plus b over d times t, and y equals y naught minus a over d times t, where t is an integer. In fact, arbitrary integer, so we see that there are infinitely many solutions. And here, what is d? D is the greatest common divisor of a and b. Let's prove this, okay? So we are gonna go back to my notepad. Okay, theorem. So I'm going to restate, what I just mentioned, okay? So suppose that A and B are non-zero integers and C is an integer, and also let x naught, y naught is, B a particular solution. Really, you don't have to use the word particular because nothing particular about it. So, you can just say a solution, okay? A solution of, or two, doesn't matter, the equation ax plus by equals c. Then all solutions of ax plus by equals c are given by x equals x naught plus b over d times t, and y equals y naught minus a over d times t, where t is an arbitrary integer. And the greatest common divisor of a and b, so that's d. Okay, that's d. Okay, so that's the statement, that's the theorem, and we're going to prove it. Okay, so I'm gonna move to next page. Okay, so proof. So we have this equation here, ax plus by equals c, and actually proof is quite easy, but and also we know ax naught plus by naught is a solution, so it does satisfy this equation, ax naught plus by naught equals c. So what I'm going to do is I'm going to subtract this. Subtract. Okay? So I have a times x minus x naught plus b times y minus y naught equals 0. Okay, so by moving this second term to the right hand side, we get a times x minus x naught equals b times, of course, I'm moving the second term to the right hand side, the sign changes, right? So it's y naught minus y. And next, what I'm going to do is dividing this equation by d, the greatest common divisor of a and b. So, a over d, that's going to be an integer, right? Times x minus x naught b over d equals y naught minus y. And this implies that since a over d divides, x minus x, the left-hand side obviously, so it must divide the right-hand side also. So a over d divides b over d times y naught minus y, and also we know a over d, we proved this, right? b over d are relatively prime and since, okay, and since these are relatively prime, so what does it say? That means a over d must divide y naught minus y. Okay, that means a over d, so y naught minus y is an integer multiple of a over d. So y naught minus y can be written as a over d times t, okay, where t is an integer. So if you solve this for y, I get that's going to be y naught minus a over d times t, and here t is an integer. Okay, so you can also see that by a similar manner, right? You can also find y. I'm sorry, x, right? So let's go and do this. So here, the b over d times y naught minus y, obviously, like, the b over d divides this, so b over d has to divide, this guy here. So b over d divides a over d times x minus x naught, okay? And also we know a over d and b over d are relatively prime, so that implies b over d divides x minus x naught. Which means that x minus x naught is an integer multiple of b over d. So x minus x naught equals b over d times some integer s. Okay, here, so s is an integer. And that implies, if you solve it for x, so x equals x naught plus b over d times s here, where s is an integer. Okay. Uh, our objective here is to find all solutions, right? So we are not going to be, this solution here is not restricted to one particular integer t. Likewise, here same, not restricted to one particular integer s. We're talking about, the so arbitrary, integer, right? Okay. So since we are trying to find the or we are trying to find all solutions t and s are arbitrary. Okay, arbitrary. This means that we can use the same letter, the same parameter, okay, the same parameter t, okay, for both for both x and y. Namely, x equals x naught plus b over d t, y equals y naught minus a over d t, and here t is in z, right? T is an integer, right? So that completes the proof. Okay, good. Okay, so we're gonna go over now, a couple of examples. Okay, first example, find all positive integers. X, I think I missed one thing. Yeah, you know what? I think I'm missing something here. Yeah, there's supposed to be an example. I know what happened. Okay, so there's another example. I think I included in this page, and then as you can see, this theorem like reach at the end. So it's just hiding. Yeah, so I'm gonna fix this. After uh, uh, you know this lecture. Sorry about that, a confusion. So the example that was supposed to show here, right, is there but hiding. Yeah, because there's no space. Is what? So right after this theorem, of course, obviously, you want to find this. So in the preceding example, we found a solution of this equation, right? A solution. So we already found it. So we wanna find the all solutions, right, of this equation. So let's get there. Oh, actually, you know what? I just realized that the proof is not complete. You know why? Because what I what I have shown is that, okay, what I have shown is if x naught, y naught is a solution of ax plus by equals c, okay, you know, uh, what is that? X and y, so other solutions, right? Other solutions, these are the solutions. So what I found out is I'm gonna carefully state that if x naught, y naught is a solution of ax plus by equals c, then x equals x naught plus b over d times t, and y equals y naught minus a over times t, where t is an integer, right, is a solution, to this equation. However, what I did so far doesn't actually tell you, listen carefully, right, that this type of solution is actually all other solutions, all right? I didn't show that. So to show you that, we will also have to. So my proof actually was not complete. Okay, sorry about that. Right, so what I have to say also is conversely, conversely, any solution, okay, any solution of the form x equals x naught plus b over d times t, y equals y naught minus a over d times t, where t is an integer, satisfies uh, this equation, okay? A x plus by equals c. This way, this is the only type. So, okay, this is the only type of solution that satisfies this equation. And therefore, these are all the solutions of this equation. So this part is also, what is that? This part it has to be also, included, right, to complete the proof, right? And by the way, I mean this can be easily seen, right? So a times x naught plus b over d times t plus b times y naught minus a over d times t equals a x naught plus a b over d times t plus b y naught minus a b over d times t, and these two guys cancel out, right? So that equals a x naught plus b y naught, and we know this equals c. So we can easily show that any solution of this form satisfies this equation here. So now finally, we complete the proof. So this completes the proof. Okay, now moving on. So moving on to example. So example, find all solutions. Okay, so find all solutions of the equation. 9x plus 24y equals 15. Okay, so solution. Okay, so we found in the in an earlier example we found what in the preceding example, I think, right? So we found x naught equals 15 and y naught equals negative 5. It's a solution, right? It's a solution. Okay. So by the theorem, above theorem, all solutions are given by x equals x naught 15 plus b over d. Here b is 24, right? And what is d? If you remember, uh, the greatest common divisor of 9 and 24 equals 3, right? That's what we found. So 24 divided by 3, that's 8. right? 24 divided by 3. 3 times 8 is 24. So it's gotta be 80 and y equals y naught negative 5 minus a over d. A over d, 9 over 3, 3t, and t is an arbitrary integer, right? So these are the order solutions. Okay, right, cool. All right, so we are going to go over now, the following a couple of examples. So first example is find all positive integers x and y such that 4x plus 6y equals 100. So let's talk about this example first, okay? All right, so here's an example. Find all positive positive solutions for x plus 6y equals 100. Okay, so to do this, to solve this, right, we gotta find one solution. Okay, so first we need to find what is that? I mean, the greatest common divisor of 4 and 6, right? That's easy. I mean, you don't have to use anything. That's 2, right? But also we need to find a solution. So let's do the Euclidean algorithm, right? So the if you divide the 6 by 4, that's 4 times 1 plus 2. So here 2 is the greatest common divisor of 4 and 6. Oh, I'm supposed to use yeah, this color, blue color. Okay, I forgot. That's all right. So 4 and 6 equals 2. And of course, so since in this case the greatest common divisor, okay, greatest common divisor 2 divides 100, okay, uh, a solution of 4x plus 6y equals 100 exists. We know that, okay? All right, so let's find the solution first. So here, if you write this for 2, so 2 equals 4 times 1, 2 equals 4 times 1 plus, oh no, actually 4 times negative 1, 4 times negative 1, that's times 4 times negative 1 plus 6 times 1. Okay, so here x naught equals negative 1 and y naught equals 1 is the solution. Okay, solution, oh no, uh, I'm not gonna use it, x naught, y naught, no, that's, I gotta use different, right, so x prime and y prime, okay? As a solution of the equation 4x plus 6y equals their greatest common divisor, right? Greatest common divisor of 4 and 6, which is 2. So 2 times 50 is 100, right? So here x naught equals 50 times x prime, which is negative 50, and y naught equals 50 times y prime, which is just 50. That's the solution. Okay, this is a solution of the original equation, right? So here 4x plus 6y equals 100. So now we are ready to find all other solutions. Okay. So all solutions are then the x equals x naught negative 50 plus a, oh no, sorry, b over d equals 2, right? D equals 2. So b over d, that's going to be 3 times t, right? 3 times t. And y equals y naught, which is 50 minus a over d, 2t. Here, t is an integer, arbitrary integer, right? These are all the solutions. But that's not the question, what the question is asking. What the question is asking is find all positive solutions of 4x plus 6y equals 100. So we have to impose the following, the condition, right? So here, x has to be positive and y has to be also positive. In other words, negative 50 plus 3t is positive. So from this we get t is, if you solve this inequality for t, t is greater than 50 over 3, right? 50 over 3 is 16 over 6, and so on and so forth. Okay, right. So, in other words, t is greater than, since t is an integer, t is going to be greater than or equal to 17. Okay. And also y, 50 minus 2t, that's going to be, that has to be strictly greater than 0, positive. So this implies that t is less than 50 divided by 2, which is 25. So this means t is less than or equal to 24. So by putting them together, right, all positive solutions are x equals negative 50 plus 3t, and y equals 50 minus 2t, where t is greater than or equal to 17 and less than or equal to 24. Okay, 24. In fact, you can, these are not many, so you can actually write out. Okay, you can write out, the these solutions. Okay, so here, the so I'm drawing a box here. One, two, three, 4, 5, 6, 7, 8, 9. So I need I need 9 columns. Oh, never mind. Okay, 9 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I don't need this part, right? Okay. Oh, okay. I went a little far. All right. So here, that's for t, x, y. So t equals 17, 17, 18, 19, 20, 21, 22, 23, 24, right? Okay. And so, for t equals 17, you can easily calculate that's going to be x equals 1, y equals 16. For t equals 18, x equals 4, y equals 14. And for 19, I have 7, 12. So here I have 10, 10. And here I have 13, 8. And 16, 6, 19, 4, and 22, 2. Okay, so these are the, all the positive solutions. Okay, now I believe this is it, the last thing I want to talk about. Okay, so the last example, a man paid $11.39 for some 39-cent pens and 69-cent pens. Okay, how many of each did he buy? Right, so that's the question, and this can be actually solved, right, using the linear combinations. Okay, right. So our last example, a man paid uh, $11.37 for some 39-cent pens and 69 cent pens. The question is, how many of each, how many of each did he buy? Okay, so here's a solution. Here's the solution. Let x and y, x and y be the number of 39-cent pens and the number of 69, okay, 69-cent pens. Then respectively, he bought respectively. Okay? Then we have the following equation. So, you know, the since 39 cents and 69 cents, you know, that's using like cents, right? So $11.30 $37 has to be also same unit, right? Cents. So we have to switch the cents. Of course, obviously, $11.37 is 1,137 cents, right? So we have the following equation: 39 cents. So 39 cents times x plus 69 cents times y equals the total amount he spent, right, to buy these two types of pens together. So that's going to be 1137, right? 1137. So we have this equation, okay? We have a Diophantine equation. So we are actually going to solve this equation, right? With the, you know, the constraint that x and y both be positive, right? Okay, so first let us find a solution, right? Okay, so if we divide this 69 by 39, so that's 39 times 1 plus 30. So I'm trying to find the, you know, the greatest common divisor of 39 and 69. And now, you know, if you divide the 39 by 30, so that's 30 times 1 plus 9. Okay? And now if you divide the 30 by 9, that's 9 times 3 plus 3. So we see that this number here, 3, is the greatest common divisor of 39 and 69. So here, the greatest common divisor of 39 and 69 equals 3. Okay, so now I'm going to work backward. So 3 equals, right? 3 equals 30 minus 9 times 3. And this equals 30 minus 9 can be written as by the previous step, 39 minus 30 times 1 times 3, and that equals negative 39 times 3 plus 30 times 4. Okay, 30 times 4. All right, now this equals, by the previous step, that's negative 39 times 3 plus, instead of 30, I'm going to replace it by 69 minus 39 times 1 times 4. So that equals here negative 4 times 39, negative 3 times 39. That's going to be 39 times negative 3, oh sorry, negative 3, negative 4, so negative 7. Okay, so negative 7 plus 69 times 4, 69 times 4. So here x prime equals negative 7.